think now you're in business. So we're going to look at matrix and vector differentiation. It's not any different from what we've been doing, but it's just in a few well-structured cases, trying to put them in a compact form. So the first example we will give is this, or the first example we'll work with. So suppose you have a function, see this function. So suppose you have exactly, this function would look something like this: a1 x1 plus a2 x2. I think it can go as far as you wish. Maybe we stop at nth variable. So this can be written as, you pick this vector a1 up to an, and then you multiply it by the column vector with the variables x1 all the way up to xn. So this vector is just a transpose. If you think of the vector a as this vector a1 to an, then this one simply now becomes, this first part is just a transpose of a, and the second part is a vector which we call bar x, consisting of these variables x1, x2 up to xn. So then you can write this linear function in compact form like this, as a vector a of coefficients, a transpose of coefficients, and then a vector with the variables as a column vector. So the coefficients will be a row vector, or just a 1 by n matrix, if you want to think of it as a matrix. Then this by x is a vector containing the variables. A simple example where of only two independent variables is given here, x1 and x2. And you have two coefficients. So if you expand it, this is what you get. So now you can think of it as a function. In this first example, it is actually a function of this form. So it picks n variables, x1 up to xn, and gives you, once you compute this, you just get a number. So it's a function that picks n numbers and produces exactly one number after that. So it's a function from Rn to Rn. So in our proper example here, or other concrete example, we are now dealing with a function from R2 to R2, or to R, sorry. So this function we're dealing with is just from R2 because we have two variables. And then when you work them out, you get just a number. So the output is just a real number. So the question is, how do you differentiate this? This function, if you get the partial derivative with respect to x1, you will get a1. I think that is obvious. The partial derivative with respect to x2, you will get a2. So the derivative of a function with respect to the vector x will simply be is a1 and a2. We learned this formula earlier, so we're just using it here. This formula for differentiating a function of n variables with respect to a vector. So this is what you get. Basically, you just have one component function, so you get the partial derivative of that one component function as yours, but the transpose of A. So this
Excuse me, Doctor, you're breaking.
You can't hear me now. Oh. Just hold on. I will meet everyone.
You're okay now.
You can hear me now.
Yes.
Yes.
Okay. So that's what it looks like. So in general, if you have this function here, if you get the derivative with respect to the vector, so remember, if you're getting the derivative with respect to the vector, you just use the ordinary differentiation. This will simply be equal to A transpose. That's what this will be. So we, like I said, we're not doing anything different from what we did earlier. We are just putting some of the common derivatives we'll encounter in a compact form. So this is a linear function, and the derivative of a linear form is just the transpose of this vector A, consisting of the coefficients A1 up to AN. And if you restrict yourself to two variables, this example restricts yourself to the example of where you have two variables, which is easier to understand, but it works in general. Okay, so the other one is I don't know if we covered the norm. The norm is just the length of a vector. I think we covered that. So it's possible to, if you have a vector X, it's possible to write its length as X transpose X. So for example, if your vector is this X1 with only two variables, this can be extended to any number of variables, but for purposes of illustration, it's faster to work with two variables. So if you get the norm of this, remember it's simply the dot product of the vector with itself. And under the norm that the standard norm that we've been, the true norm, that's what we call it, or the L2 norm, if you like, will simply be given by the square root of x1 squared plus x2 squared. If you want to get the norm squared, then you just drop the norm squared of this vector is simply x1 squared plus x2. Now you drop the square root because you're squaring both sides. And you can see this norm is just a function of two variables. If you look at it, the square of this norm is just a function of two variables. So anytime you have some function expressed in that form, then you can get the partial derivative again will simply be the partial derivatives of this function with respect to x1, it will be 2x1, which becomes the first entry of your derivative. And with respect to x2, it will be 2x2, which becomes the second entry in your derivative matrix. But then this is the same as just 2x1, x2, which is the same as 2 times x transpose. Squared of a vector. So essentially what we are saying is that d f over d by x for this example is simply equal to times x transpose. Is it making sense so far? So there's some resemblance to what you see when just working with ordinary derivatives of polynomials. It's just that now we are working with matrices. So this, there is a, if you have an additional constant in your linear function, if you have a constant b added to the linear equation, it becomes an affine function, what we call the affine function. But the constant will just vanish. So the derivative won't be very different from the first case. It will just be A transpose. You can test this by doing the expansion yourself and seeing that indeed it works. Because B does not have any impact when you do the differentiation. It will vanish for all derivatives. So you still be left with just the transpose of A as your derivative. So this affine function is essentially the same as a linear function, but we have a constant term added. That's it. So the other one that we'll look at now is this quadratic form. So the quadratic form is simply in that form where you have the vector multiplied by a square matrix, and then multiplied by the vector on the left. So you have a transpose on the left, the square matrix in between, and the same vector repeated on the right, but now not as a transpose. So again, this is just a number. When you work this out, you'll get one number. So this again is simply a function from Rn to R. You can confirm that this is a number by looking at dimensions. X transpose will be n by 1 multiplied by n by n, which will give you an n by n. Then you have a 1 by n by 1 now. So you'll end up with a 1 by 1. So you have 1, I think you'll have 1 by n multiplied by n by 1. You end up with a 1 by 1, which is just a number. So you can still think of it as a function from Rn to itself. Now, there's a bit of work. If you want to do it in full, you can. Eventually, if you do the derivative, depending on whether the matrix is symmetric or not, you will get a different answer. So if it's not symmetric, this is what you get when you get a partial derivative of this function, not the partial, just the derivative of a function with respect to the vector x. This is what you will get, A plus A transpose. And then on the outside, we'll have the transpose of a vector x. So this is if the matrix is not symmetric. If the matrix is symmetric, then A and A transpose are the same. So it simply reduces to this. Because a symmetric matrix, the transpose is equal to the matrix itself. So this, they become twice the same matrix, and that's why you have the 2. That's your answer. So I recommend that you try this for a simple case. So for example, you can pick a 2 by 2 matrix. So if you pick a 2 by 2 matrix, then your variables will be 2. So X transpose will be here. You'll have your matrix here, A11, A12, then A21, A22. So you have your matrix, and then on the other side, you have your X1, X2 vector. So if you multiply this out, you will get some expression, which is just a number. That expression will be your function. And then you can apply the same ideas of getting derivatives you'll be fine. The same ideas we applied earlier, because now you just have a function which is real valued. Then you can compute the derivatives, and eventually with some manipulation, you will see that this is what you get. So in particular, if you want to, and then now the next is just a corollary. If it's a symmetric matrix, A and A transpose are equal, so you have twice A in the derivative. So what's down here? Oh, there's some people still joining. Can remove the camera. Maybe it's the one. You can still hear me clearly.
Yes.
Okay. So now you will notice a bit of a difference. Here we are getting the gradient. And up here we had the derivative. Remember the first derivative is just the transpose of a gradient. So if you get the gradient, you instead get the transpose of this. So given if A is symmetric, then the transpose of A is equal to A. So this won't change. So this is assuming A is a symmetric matrix. This last part assumes A is a symmetric matrix. So the gradient will now be the transpose, because the derivative is a transpose of a gradient. At least the first derivative is a transpose of a gradient. So the gradient here will simply be the transpose of a first derivative. You recover it by just getting the transpose of the first derivative. So the Hessian matrix is simply the derivative, the second derivative of your function f. So you treat this as a vector valued function, and then just get the derivative to get a matrix. So the derivative of 2ax, if you have A as a matrix, is just 2a. So again, you can try this with two variables, expand it and work it out to see why that works. So this matrix has some interpretation. You can use it to define the curvature and determine whether your point is a global or local minimum or maximum as well. That can happen. So that will become clearer when we move to convex functions and convex optimization. Are there any questions on this? I have shared this with the class rep, so you will have a copy of this. But I suggest for every example here, you try to work it out with a small example where you have only two variables and expand everything and do the differentiation exactly as we learned in the first part, and everything will fall in place. So this matrix differentiation will be useful when we move to applications. When we see how the optimization is done, for example, for linear regression, you will see that it's convenient to work with the matrix differentiation. So I don't know if there are any questions for this. The screen is now a bit dirty. Let me clear it so that And then the other thing, I may have mentioned this at the beginning of the class. If you want to understand this mathematics, please do not stare at what I am sharing on the screen. Pick out your pen and notebook and write things down. If you don't write things down, you will not remember them. That one I can guarantee you. You make a habit of writing things, then you will see my point. So it appears there are no questions on this section, but I recommend a lot of practice. They look simple when they're being done on the screen, but they can quickly look very foreign when you try them on your own. So that's why the best time to try them is while you're in class, and any problem you encounter, you have it resolved while you're still in class. It's harder to do it later. And then you could also look for books that cover this. There's a lot of material on this kind of stuff. I will share a book on calculus. The problem is sometimes the books don't cover things exactly as. No, but there's one good one by K.G. Bidmore for calculus. I will share that one. Good. So I think now I can move to the next part. I think I need to move back to functions of two variables, but now we talk about the convex and concave functions. So we start by defining a convex function. So first we can just read through what it says here. So it says, we'll say a function, a real value function, is convex if the line segment between any 2 points of the graph lies above or on the graph. So those are the important words. The two words here that are really important are above or on the graph. If you are thinking in just the 2 dimensions, it's simple. This is what it will look like. So it looks like a bakuli. So if you pick any 2 points, a line joining them will be, it doesn't matter which 2 points you pick, the line joining them will be always above. So in this case, we have a convex function. So this, if you move to 3 dimensions, it will look like a bakuli now, something like a bakuli. So if you pick any 2 points inside the bakuli and join them by a straight line, the straight line will be completely above or on the surface. Are we together? So this is what we mean by convex. So over and above that, there's a second part or a second concept we need to look at, and that is a concave function. Again, we consider a real valued function. It will be concave if any line segment between any 2 of its points, again, will lie below or on the graph. So I think that should be easy for you to figure out. So concave will be facing downwards. Something like that. That's concave. Doesn't have to be a smooth curve. Even this is concave, even if it's just with a corner there. And then if it's in 3D, where we can still draw, it would look something like a bakuli that is turned out upside down. And pick any 2 points inside there. If you join them with a straight line, the line stays entirely either below or on the graph. So this now becomes concave. The second example. Are we together?
Yes.
Okay. So you need to get the distinction. At the top, we're talking about convex and concave function. Now we are talking about convex set. So you can also define the concave and convex functions in terms of convex sets. I don't know if I have done that later, but we'll check. So a convex set, so this can be defined in higher dimensions as follows. So a convex set in RK is a set where if you pick any two vectors, say X and Y, from the set, this vector V X plus T by Y minus X, where T is a number between 0 and 1, is lies entirely in the set, right? So for example, if I have another way to look at it, I will avoid, I'll just use diagrams. Another way you can look at it is the following. So if I have, say, an object that looks like this, for it to be a convex set, what it means, you see, the set now consists of the things that are in the interior of this boundary. So if I pick a point inside here, another point here, and I join them with a straight line, part of the straight line is outside the set. So this one is not convex. This one fails to be convex. It is not a convex set. But if I have something like this, for this one, probably doesn't matter what I do. Any 2 points I pick inside and join them with a straight line, the straight line would be entirely inside the set. So that's the geometric interpretation of this statement. It can be proved algebraically as well. I am just avoiding the additional algebra. So in the first example, we're talking of a convex set. So now you can define a function, a convex function or concave in terms of this convex set. So a function will be convex if the set of points lying above or on the graph will be a convex set. So again, if you go back to our examples, look at the convex set. The points lying above or on the graph form a convex set because if I pick any 2 points in there and join them, the line will entirely be in the set of points that are above the graph. So if the set of points form a convex set, the set of points above form a convex set,